Welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Dom Briones, I messed that up, Dom Briones, there we go, from Nanyang Technological University. He'll tell us about equiangular tight frames from fusion schemes. Take it away, Dom.
Okay, great. Thank you for the introduction, Dustin. So I'll be talking about ETFs from fusion schemes, and this work is ongoing with Gary Greaves and Jesse Lansdowne. So the gist, the big idea that we're trying to show in this talk is that we're going to find gram matrices of equiangular tight frames using these objects called association schemes. So an association scheme is just a collection of matrices with certain properties. And in particular, from an association scheme, we can get these idempotent matrices, which we can add together, and these give us gram matrices. And these gram matrices track inner products of certain vectors. And from this gram matrix, we can recover these vectors, such as these vectors over here in this tetrahedron. And those vectors have special properties, which turn them into what's called an equiangular tight frame. So again, we're using association schemes to find these gram matrices of equiangular tight frames. So the idea is for the flow, we start with what are ETFs, we motivate them, and then what are the gram matrices of ETFs, and how we can obtain these from association schemes. Next, we'll focus on the narrative with the real case, how we can find real equiangular tight frames or their gram matrices, and the association schemes which can produce these objects. In particular, we'll see that the considerations actually reduce to just two class symmetric association schemes in this case, which are equivalent to certain strongly regular graphs. And finally, we'll use this notion of fusion schemes, where we add the matrices in an association scheme together to somehow limit our search space. And we'll apply it in a different way, in particular, to show that certain three-class association schemes give us or allow us to recover an interesting family of gram matrices that were found by Jasper, Iverson, and Mixon. Okay, so first things first, ETFs from association schemes. So what's an ETF? Well, let's say we have a bunch of lines in space and we want to pack them together. So there's bad packings and there's good packings. So what we're going to do to kind of measure how good or bad the packing is, we're going to take a bunch of representative vectors from our lines, and we're going to make them or select them to be of equal norm. Now, the sharper the angles between the lines, the larger the modulus of their inner products. And what we want to do is to minimize the maximum of these inner products, or the modulus of these inner products. So this is this quantity here is called the coherence. And what we want to do is minimize that. It turns out that this is minimized precisely when we have an equiangular tight frame. So here's our setup. We have a bunch of vectors in space, the phi's, and often I'll put them as column vectors of a short fat matrix, like the one we see above. We're going to assert that these guys have equal norm, and the quantity that we want to minimize over here, that's bounded by this quantity on the right, and this inequality is called the Welch bound. Turns out that we have equality precisely when our collection of vectors form an equiangular tight frame. Now, what does that mean? Well, from the words, we have, for our collection of vectors, they have equal norms, and they have equal angles, hence equiangular, and we have what's called tightness. In terms of the matrix representation, the short fat matrix that we have here above, this just means that our rows are orthonormal. So those are the three properties that we want to have a nice packing of lines: equal norm vectors, equal angles, and tightness. So here are some examples of equiangular tight frames. The upper left one is just the Mercedes-Benz frame. The next one is just some vectors from a facet of the icosahedron. There are 6 of these. And here phi is just the golden ratio. And then we have at the bottom an example of a complex ETF, which isn't as easily graphically represented. And here omega is just a 7th root of unity. So these are just examples of ETFs. Now, what we want to do is translate the problem of looking directly for the vectors of an ETF into looking for what are called gram matrices. If I have a collection of vectors, I can just take the inner products of these vectors and then track them using a matrix, and this matrix is called the gram matrix. Now, the properties of an ETF translate into properties of the gram matrix. So equal norms mean that my gram matrix has a constant diagonal. Tightness translates to my gram matrix being self-adjoint and idempotent. And equal angles for my ETF translate to common modulus off-diagonal entries in my gram matrix. Now, interestingly, if I have a matrix that satisfies these properties on the right, it actually has to be the gram matrix of an ETF. And from this gram matrix, I can actually recover an equiangular tight frame. So instead of looking for ETFs directly, we're going to be looking for gram matrices. As an example, here's an ETF, the Mercedes-Benz frame, and its gram matrix here on the right. So constant diagonal, common modulus off-diagonal entries, and it's self-adjoint and idempotent. Now, let's motivate this tool of association schemes through this example. We're going to give a family of ETFs called harmonic ETFs. We're going to give a construction, and then we'll obtain its gram matrix through association schemes, because this is a method that generalizes to more than just abelian groups. Now, our harmonic ETF arises from an abelian group by taking the DFT matrix from that abelian group. Say Z7, for example, cyclic group of 7 elements. Here's its discrete Fourier transform matrix. And with an appropriate choice of rows, we actually obtain an equiangular tight frame, such as this one. And from this equiangular tight frame, we have this gram matrix, which is circulant. And what I'm going to do now is I'm going to show you how we can recover this gram matrix using essentially what are association schemes. But let's take this step by step. So let's say we have an arbitrary circulant matrix, such as this one on the left, and I want this to be the gram matrix of an equiangular tight frame. Well, being circulant, I can diagonalize it using the discrete Fourier transform matrix, and it diagonalizes to this matrix on the right with some eigenvalues. But here's the key thing. If I want the matrix on the left to be the gram matrix of an ETF, its eigenvalues have to be 0 or 1. Let's say this one over here. But the thing is, if I just randomly put 1s and 0s in whichever places, it's not always going to give me the gram matrix of an ETF when I pull back by the discrete Fourier transform. And yet, with a good choice of 1s and 0s in just the right places and with the right amount of 1s, I can actually recover our gram matrix from before. So what's going on here? What's happening? What's the underlying kind of idea and structure? Well, let's think of it this way. On the right, I have 1s and 0s on my diagonal. So I'm kind of thinking of building this matrix using 0-1 matrices, such as this collection on the right. So this is just the basis of the diagonal matrices. And it turns out, if I pull them back by the DFT, I'll get the following matrices here on the left. Now, the entries aren't too important. Let's just note that they are self-adjoint and they're idempotent and they have constant diagonal entries. In fact, these matrices on the left, they are gram matrices of tight frames, but not necessarily equiangular. But if I add the right idempotents here on the left together, that actually gives me the gram matrix of an equiangular type frame. And that's the key, adding these certain idempotent matrices together, which gives me the gram matrix of an ETF. And thus, to answer the question, well, where do these things come from and which ones do we add together, enter the concept of the association scheme. So an association scheme is a collection of 0-1 matrices which commute and are closed under transposition, such that the first one is the identity, and these all partition the all-1 matrix. And importantly, the linear span is closed under matrix multiplication. So the linear span isn't just a vector space, it's actually an algebra. Now here's the thing. These matrices are normal and they commute. That means they're simultaneously diagonalizable. And in particular, if I take the maximal common eigenspaces and take the orthogonal projections to those eigenspaces, I get these matrices over here. These are orthogonal projections to the maximal common eigenspaces. And what's interesting is that these actually form an alternative basis of the span of our matrices from before. They have the same span, but it's a different basis. And these elements are self-adjoint, they're idempotent, and they have constant diagonal. In particular, they're gram matrices of tight frames, but they're not necessarily equiangular. As we saw before, by clever choices of adding together some of these idempotents, I can get an equiangular tight frame gram matrix. So a natural question is, which subsets do I take so that the sum of the corresponding idempotents is the gram matrix of an ETF? And this was posed and investigated by Iverson, Jasper, and Mixon in 2020. We'll give an answer to this in terms of what's called the change of basis matrix. So just recalling our setup, we have an association scheme. So these matrices in red, and then we have these primitive idempotents, which span the same linear space as our association scheme. So these are two bases of the same linear space. We can change between one basis and another using the change of basis matrix. So just the usual concept of a change of basis. So for instance here, according to this change of basis matrix, E0 is just A0 plus A1 plus A2, and then scaled by some factor. So how do we use this to determine which gram or which idempotent matrices to add to give me the gram matrix of an ETF? That's given here. So the following are equivalent. If I have a bunch of idempotents and add them together, this will be the gram matrix of an ETF precisely when these things over here have the same moduli. Now, this is easiest to see with an example, so let's do that. Let's say I want to check if E1 and E2, adding those together, if that will give me the gram matrix of an ETF. So I'll start with my change of basis matrix over here, and then I'll add the first column and the second column. We start the indexing at 0. So I add these columns together. And then all I have to do is check that aside from the first entry, the other entries have the same modulus. So in this case, -1 and -1. Of course, they have the same modulus since they're equal. And that's all I need to check. That means that E1 and E2 is the gram matrix of an equiangular type frame. The proof behind this is as follows. So the top entry actually gives me the diagonal entry of my gram matrix, and the other entries actually give me the off-diagonal entries. So to have equiangularity, I just need these off-diagonal entries, or these entries below the first entry over here. We just want them to share a common modulus. And that's it, really. As a more complicated example, here's the change of basis matrix from an association scheme with 21 classes, or in other words, 22 matrices inside the association scheme. And this is an example we'll see again later, and an example found by Jasper, Iverson, Mixon. So if I select these columns in red, and I add them together, mush them together, I'll get this column vector over here. And aside from 28 at the topmost entry, every entry has a modulus of 4. That tells me that the sum of the corresponding idempotents is the gram matrix of an equiangular tight frame. And that's shown by this matrix over here, graphically represented. So this is a complex ETF of 64 vectors over a dimension 28 space. Moving on, here's another example, this time a real ETF gram matrix. So we have here the gram matrix. It's in the span of this association scheme. It's a linear combination of these matrices, and indeed, it is the sum of the following primitive idempotents of that association scheme. Now, speaking of real ETFs, we'll use this as a sort of jumping point. Let's talk about real ETFs that can be obtained from association schemes. It's a bit of a spoiler. We'll see that essentially looking for ETFs from association schemes, or real ETFs from association schemes, it boils down to looking at symmetric two-class association schemes with certain parameters. Now, here's kind of the overarching story for this part of the talk. Morally, the following notions are equivalent. So at the moment, there's a bunch of terms here that we've not defined yet, or might have not encountered yet, but we'll go through these one by one to kind of give us this idea that these things are indeed equivalent. And then we'll focus particularly on symmetric two-class association schemes. So first things first, if I get the gram matrix of a real ETF from what's called a symmetric two-class scheme, in other words, it's a sum of idempotents of a two-class scheme, then it can be obtained as something in the span of the association scheme. Now, this is just really a problem of terminology. So a two-class association scheme means that there's two other matrices outside of the identity in my association scheme. Now, if I can recover a gram matrix using the idempotents of my association scheme, it is certainly a linear combination of the adjacency matrices here above. And that really shows the first of these arrows. So nothing much to talk there. Now, for something more interesting, we have this next arrow over here. If I have the gram matrix of a real ETF that comes from the span of an association scheme, it's actually a real equiangular tight frame with a certain kind of symmetry, and this is called centroidal symmetry. So let's talk more about that. We call an ETF centroidal if its gram matrix has the all-one vector as an eigenvector. Geometrically, it has a kind of symmetry with respect to a centroid or with respect to an axis. But algebraically, we can just say that the all-one vector is an eigenvector of the gram matrix. Now, if I have a gram matrix that is in the span of an association scheme, it is automatically centroidal. The reason being is that the gram matrix is in the span of the association scheme, and every matrix in my association scheme has the all-one vector as an eigenvector. There's a quick way to see this. So it suffices to show that if I take any matrix, say AH in my association scheme, I just need to show that it has a constant row sum. So if I add the entries of any given row, it's the same as taking the sum of any other row. So to do that, let's fix a matrix, let's say AH, and let's consider the sum of the entries in the ith row. That's just the II entry of this matrix, AH transpose, but this is in the span of the association scheme. So it's a linear combination of the things in my association scheme. In particular, it has a component that corresponds to the identity matrix. So all of the diagonal entries are equal to Z0. In other words, if I take any row whatsoever, take the entries of that row, the sum is always C0, and thus the claim is shown. Now, moving forward, turns out that real ETFs with centroidal symmetry will correspond to certain strongly regular graphs having these parameters. And let's talk about these strongly regular graphs and these parameters right now. So a strongly regular graph is, well, just a graph with V vertices that satisfy these certain properties. Every vertex is adjacent to K others. If I have two adjacent vertices, they have lambda common neighbors, and non-adjacent vertices have mu common neighbors. So for instance, for this example, every vertex is adjacent to 10 others. And adjacent vertices, like these two orange ones, they have 6 neighbors in common. And non-adjacent vertices, such as these two orange ones, have 6 common neighbors. So those give us the parameters of our strongly regular graph. As it turns out, by work by Ficus, Jasper, and these other authors below, an SRG, or a strongly regular graph with these parameters, correspond to a real ETF with centroidal symmetry. We're not going to go too deeply into this, but here's kind of the idea. If we start with the gram matrix of our real equiangular tight frame with centroidal symmetry, we can replace the positive entries with 1s, we can replace the negative entries with 0s, and then we can just remove the diagonal. And this will give me a 0-1 matrix, and it turns out this will be the adjacency matrix of a strongly regular graph. Conversely, starting with the adjacency matrix of such a graph, we can appropriately translate the diagonal and scale everything around to give us this ETF with centroidal symmetry gram matrix. So that's kind of the rough idea of this correspondence. Now, finally, the last arrow that we're looking at. If I have a strongly regular graph with certain parameters, then we can actually get this gram matrix of an ETF from what are called these symmetric two-class association schemes. And again, this is really more a matter of terminology, because what happens is, if I have an adjacency matrix of a strongly regular graph, then these 3 matrices over here, the identity, the adjacency matrix, and sort of the complementary matrix over here, this will always be a symmetric association scheme. So for our example, here's the adjacency matrix, the identity, the complementary matrix, and this forms a two-class association scheme. And conversely, if I have a two-class symmetric association scheme, then this matrix over here will be the adjacency matrix of a strongly regular graph. And here we have a result essentially by Lemons and Seidel that we recover through this perspective of getting the idempotents from an association scheme. So we have a symmetric two-class scheme so that the adjacency matrix A1 is that of a strongly regular graph. Then E1 or E2, the primitive idempotents of my scheme, they're gram matrices of ETFs precisely when the strongly regular graph satisfies this equality in its parameters. So the idea is we use our criterion using the Q matrix, and we can express the Q matrix or the change of basis matrix in terms of the parameters of the strongly regular graph. And this restricts, in fact, necessitates the eigenvalues of A1 to be certain values. And finally, these will force, essentially, the number of vertices to satisfy the equation that we expect. And that's kind of the idea of it all. So we've seen this equivalence between two-class schemes and strongly regular graphs of certain type and these real centroidal ETFs. But here's what I want to emphasize in particular. Oh, here's another example. And here's what I want to emphasize in particular. What actually happens when we're looking for these gram matrices of real ETFs, and we're looking at them in symmetric association schemes, there's no need to go any further than symmetric association schemes with two classes. And to explain this a bit more thoroughly, let's say we have a symmetric association scheme with however many classes we have. And let's say that we have obtained, as a sum of idempotents of this scheme, the gram matrix of a real equiangular tight frame. Then I can actually obtain the same gram matrix from a symmetric two-class association scheme. So there wasn't really a need for me to look at the symmetric scheme with however many classes. It suffices to look at something with two classes instead. And the moral of this is that in the symmetric case, or when we're looking for real ETFs, we need only consider two-class association schemes. So we've kind of reduced the search space from however many classes of a symmetric association scheme to symmetric association schemes with only two classes. And this reduction kind of allows us to motivate this idea of fusion. And this brings us to this last section, which I want to spend the most time on, ETFs from fusion schemes. So let's get started. The idea behind this, and as we've seen motivated in the prior section, was perhaps it's worth considering association schemes with few classes when we're looking for gram matrices of ETFs. And the main result of this section is that we can get gram matrices of ETFs from three-class association schemes, from certain three-class schemes, and in fact, we'll recover an interesting family of gram matrices that are obtained from association schemes derived from Suzuki 2 groups. So this is an interesting family of gram matrices that we can actually recover from this technique. So first off, what's fusion? Well, from the name, we're just going to add adjacency matrices together, and if that turns out to be an association scheme, we call that a fusion scheme. So here we have an association scheme up top. Let's add A1 and A2 together, and A3 and A4 together. This gives me another association scheme over here. And when this happens, we call the scheme at the bottom a fusion scheme of the association scheme at the top. So each adjacency matrix at the bottom is a sum of adjacency matrices at the top. And here's an observation. So here's the primitive idempotence of the original association scheme. Here at the bottom is the primitive idempotence of the fusion scheme. And notice that the idempotents also fuse together. So in this case, E2 and E3 fuse together to become E1 tilde. And now I highlight this thing. E2 plus E3 is actually just E1 tilde, and it's the gram matrix of an ETF. It's the exact same gram matrix that we've recovered from the fusion scheme. So instead of having to look at a scheme with 5 matrices, I could have actually just recovered the same gram matrix from a two-class association scheme. And indeed, instead of having to combine two different idempotents, I could just recover it from a single idempotent. So in this sense, we kind of reduce the search space. And in this sense, we kind of simplify that search. So with this tool, a natural question is, well, if I'm going to use this fusion idea, when can I identify fusions? When do fusions occur? How do I find them? Well, this is answered by the dual Banach-Muzzi criterion. Dual because we're focusing on the idempotents instead of the adjacency matrices, which is natural since we're using the idempotents to make the gram matrices. Okay, so let's try to make this naively, and then we'll talk about the more formal statement of the criterion. So the idea is we're going to add some of the primitive idempotents together, let's say E2 and E3, and E1 and E4 to form E1 and E2 tilde, respectively. And then I'm going to check that these new idempotents are closed under transposition. So far, so good. Now, the tricky part is the next one. I want to combine the adjacency matrices such that my new idempotents here at the bottom are in the span of these new adjacency matrices. So I want my fused idempotents to be in the span of these fused adjacency matrices. And I want these fused adjacency matrices to be the same in number as my fused idempotents here at the bottom. So 3 fused idempotents, 3 fused adjacency matrices. One way to do this might be to look at the level sets of E1 and E2, for example, and this might suggest which adjacency matrices you can take. But unfortunately, we can't always combine the adjacency matrices in this way. And so we kind of need a way to conveniently check when this is possible. Lucky for us, and this is the criterion, we can use the change of basis matrix to do exactly that. So same thing, we're smashing together or fusing together E2 and E3 and E1 and E4. We'll look at the Q matrix or the change of basis matrix. We'll add the corresponding columns that correspond to our primitive idempotents. They'll add together over here and over here. And now we're just going to merge the equal rows. So if the rows are the same, we'll just merge them together. And if the number of rows is the same as the number of columns, in other words, if we get a square matrix after this process, then congratulations to us, we have a valid fusion association scheme. And with this method, we actually get as bonus information which idempotents we've fused together, which adjacency matrices we should fuse together. And this matrix that we got as an end product is actually the change of basis matrix of our fusion association scheme. So we get all of that information through this technique or through this dual Banai-Muzychuk criteria. Okay, so here's an example now using a complex Equiangular type frame, because we'll be looking at complex ETFs from here on. These are the adjacency matrices. We smush the ones that are red together, the ones that are blue together, and indeed, the idempotents will smush together as well. The blue ones add to this one, the red ones add to this one, and the blue ones will give us the gram matrix of an Equiangular type frame. Okay. Now we'll be using fusion in a slightly different way. So prior, we showed that we can reduce the search space, and then using the dual Banai-Muzychuk criterion, we can actually infer information about the fusion using information from the original scheme. But now, what we're going to do is we're actually going to use fusion to determine some information from the original association scheme. And we'll see how this applies to the case where we have three classes. So here's the idea. If I have any association scheme, I can pair every matrix in my scheme with its transpose and then add those two together. And this forces me to get a symmetric fusion association scheme. So this will always be an association scheme, and it's by construction symmetric. So for example, here I have A1 and A2 are transposes of each other. I smush them together, add them together, get this matrix at the bottom. And from a 3-class scheme, I have this 2-class association scheme at the bottom. And in fact, there's something special that happens when I have a 3-class scheme and do this process. Because if I have a 3-class association scheme, so 3 matrices aside from the identity, its parameters are actually determined by the symmetrization, which is this 2-class scheme over here. In general, if I have a 3-class non-symmetric association scheme, there will always be 2 of those that I can pair, and that will give me a 2-class symmetrization. Moving forward, this is just to fix our notation. When we have a non-symmetric association scheme, we're just going to assume that A1 and A2 are the ones that will be paired together when we symmetrize. And in fact, when we have a 3-class non-symmetric scheme, 2 of the idempotents will also add together in the symmetrization. And we're just going to assert that these are E1 and E2. So we're just fixing an ordering so that A1 and A2 are the ones that add together, and E1 and E2 are the idempotents that add together. Again, there's no information loss here. There's no loss of generality. We can just order things around so that these first 2, A1 and A2, and E1 and E2 are the ones that pair together. So here's our result in its generality. Let's say we have a non-symmetric association scheme with 3 classes. And let's say that A1 and A2 pair together in the symmetrization. And in particular, this will be the adjacency matrix of some strongly regular graph with some parameters. Further, E1 and E2 will come together to become an orthogonal projection of an eigenspace of A1 plus A2. And let's just say that it projects to the eigenspace corresponding to this eigenvalue theta. And that's our setup. It turns out that if we work with the Q matrix, or the change of basis matrix, we can find that E1 and E2 are gram matrices of equiangular tight frames if and only if the trace of this matrix, of this projection, of this eigenspace of A1 plus A2 satisfies this equality involving the parameters of our, strongly regular graph. This situation becomes particularly nice when A1 plus A2 is the adjacency matrix of a certain kind of strongly regular graph. And that's what we'll focus on. So these are called regular complete multipartite graphs. So these are just a certain kind of strongly regular graphs, which are graph complements of a union of complete graphs. This is a lot easier to digest with an example. So for instance, this graph over here, it's the complement of 4 copies of K4. So it's the complement of 4 copies of the complete graph on 4 vertices. And what I mean by that is that we have 4 sets of independent sets. We have these blue ones, these red ones, these orange ones, and these green ones. Let's say, pick a color, let's say blue. No blue vertex is adjacent to any blue vertex. It's an independent set. And yet, every blue vertex is adjacent to every vertex of every other color. Same thing with the reds. No red is adjacent to any red vertex, and yet it's adjacent to every vertex of every other color. So very concretely, it's the complement of a bunch of complete graphs, or more technically, it's a complete multipartite graph. Moving from this, if our setup, or with our setup from before, and with the theorem from before, things simplify a bit under this situation. So again, we have a non-symmetric association scheme so that we add A1 and A2 together for the symmetrization. And let's say this will be the adjacency matrix of a complete multipartite graph. Now, let's say that the primitive idempotents add together for E1 plus E2, and this projects to the kernel of A1 plus A2, or in other words, the 0 eigenvalue of A1 plus A2. Then it turns out that E1 and E2 are gram matrices of ETFs if and only if K is U squared minus U. Another way to put this is that our complete multipartite graph is a complement of U copies of KU, or U copies of the complete graph on U vertices. For instance, here, where the situation occurs, this is 4 copies of K4, or the complement of 4 copies of K4. Put in a different way that may be slightly easier to digest, there are certain kinds of graphs, which are called complete multipartite graphs with certain parameters, where if I take its adjacency matrix over here, I can split it into 2 parts. And this will give me an association scheme that produces gram matrices of complex equiangular tight frames. And these 2 come in pairs that are complex conjugates of each other. And that's the idea. And we highlight this idea in particular because there's a family of 3-class association schemes that satisfy this premise. Here's one such example, or the change of basis matrix of one such example. And this will yield the gram matrix of a complex ETF with 64 vertices, or 64 vectors over a 28-dimensional space. And indeed, this is the exact same gram matrix that is produced by some larger 21 class association scheme. And here's that gram matrix. It's the same gram matrix that we've seen before. And indeed, this is an example that comes from a family of groups called the Suzuki 2 groups. So in this case, the Suzuki 2 groups produces a 21 class scheme, and choosing appropriate idempotents gives me the gram matrix of an ETF. And it's the same gram matrix that can be recovered from a 3-class scheme from splitting a complete multipartite graph. So here's the kind of gist of it all. The gram matrix of an ETF obtained from the Suzuki 2 group association scheme is a gram matrix of an ETF that can be obtained from splitting a complete multipartite graph, or a certain complete multipartite graph. And I want to add some additional context into what's happening and why this is important and interesting. So groups in general, so if I have any group, abelian or non-abelian, this will produce an association scheme. And this allows us, as investigated by Iverson, Jasper, and Mixon, to have an analog of a construction for harmonic ETFs that applies to non-abelian groups. And in particular, they found an infinite family of non-abelian groups that will produce these ETFs as a consequence of their process. And in particular, these association schemes are from these groups called the Suzuki 2 groups. So this is kind of an infinite family of ETFs or gram matrices of ETFs that are analogous to the harmonic ETF construction, but this time for non-abelian groups. And it turns out we can recover the same gram matrices through splitting certain complete multipartite graphs. To end this, I want to talk about these certain complete multipartite graphs just a little bit more. So our setup is we have a non-symmetric scheme such that A1 and A2 fuse together to become a complete multipartite graph, which satisfies this condition. Or in other words, our complete multipartite graph is the complement of U copies of KU. Then it turns out, so this is just a bunch of words at the moment, it's the adjacency matrix of a certain kind of directed graph. It's a type 2 doubly regular UU team tournament. These parameters, U and U, just say that my graph is the complement of U copies of KU. And doubly regular team tournament just means that I am an orientation or a digraph of this complete multipartite graph. It's an orientation of that. And type 2 and doubly regular just means that it satisfies certain parameter restrictions or conditions. And it turns out, by work from that's mentioned in Jurgensen, Jones, Klin, and Song, I think it's also done by Klassen, is that doubly regular UU team tournaments of type 2, they're equivalent to what are called skew Bush type Hadamard matrices. So we have this sort of correspondence as well. Okay, and I'm ending with a slide. Again, essentially, we were just looking for the gram matrices of ETFs from association schemes, and we used harmonic ETFs to motivate this study. We looked at how real ETFs come from association schemes and how the situation reduces to certain 2-class schemes. And we used that as motivation for looking at fusion schemes, and in particular, how we can obtain this interesting family of gram matrices of ETFs using 3-class association schemes. So that's about it for my talk. Thank you very much for your attention and your time.
All right. So in Codex tradition, we're going to thank you by clicking buttons. I'll stop the recording here.